Pre-algebra lesson 12, prime numbers and composite numbers and products of prime numbers. So first we have to understand what a composite and a prime number is. A composite number is a number that has multiple factors. Like for example 6, you can make the number 6 by multiplying 3 and 2, or 1 and 6. Or if we think about this in my favorite terms of multiplication as an area, right? We can make a square with an area of 6 having sides of 2 and 3 to get 6, or we could have one with sides of 1 and 6 to get 6, right? Different squares. So composite numbers can be made up of different sized squares. Excuse me. Prime numbers, however, only have one option for their square, which is 1 and the number. So for example, a prime number like 5, if I wanted a square with an area of 5, I would have to have 1 and 5. Right? There's no other whole numbers I could put on these sides to multiply it to 5. Right? That's what makes it prime. And we can see the word definition of that here. A prime number is a whole number greater than 1 whose only number factors are 1 and the number itself. Or if we were to draw it in a box, a composite number can be created by multiple size squares. A prime number can only be created by 1 and itself. Now, if you look in your book on page 45, we have prime numbers 1 through 40, right? We can also use divisibility rules to help us spot prime numbers. So here's all the numbers 1 through 40, and they want to write all of the ones through that are prime. So it is the 1 through, they cross out the number 1 because by definition the number 1 cannot be a prime number. 2 is the only even prime number, so that's a fun little piece of trivia that would be good to know. So 2 is the only even prime number because once you get up to the number 4, that's divisible by 2, right? And then 3 is prime because 1 and 3. 5 is prime, 1 and 5. 6 we just saw cannot be prime. 7 is also prime. No other divisors into 7. 8 is divisible by 2, so it cannot be prime. 9 is divisible by 3, cannot be prime. 10 is divisible by 5 and 2, cannot be prime. 11 is prime. 12 can be divided by 3, 4, 2, 6. 13 prime. 14 can be divided by 2 and 7. 15, 3, 5. So you can see how we go through, we use our quick divisibility rules to find out whether or not a number is prime. What you'll notice is as you go higher and higher, the number of prime numbers in each set of 10 gets smaller and smaller. So for example, from 11 to 20, we only have 1, 2, 3, 4. We have 4 prime numbers. From 21 to 30, we have 1, 2. We only have 2 prime numbers. 31 to 40, we have 2 prime numbers again, right? So the prime numbers will kind of go down in each set of 10. As you get higher and higher, it gets harder to find prime numbers. But these are the first prime numbers between 1 and 40, and that's how you would find them. Now, let's talk about products of prime numbers, right? Or what some people would call factoring, right? So products of prime numbers are a way to rewrite a number using only its prime equivalents. So for example, let's say I have, we'll start with a small one. Say I have the number 12, right? And I want to rewrite the number 12 as a multiplication problem made out of only prime numbers. Let's see, am I going the right way to focus here? Whoops. Right? So what I want is I want to know what prime numbers will create the number 12. The way I do this is I am going to divide using my divisibility rules, and the goal is to divide by only prime numbers. So if we look at our prime numbers lower than 10, that would be like 2, 3, 5, 7. You know, those are the main numbers we want to divide by. So there's 2 ways I can do this. I can either use the division tree or factor tree method, or I can use a division tower, right, where I'm going to divide up. Now if I use the factor tree method, I can ask myself what prime number is 12 divisible by, and I know that it's divisible by the number 2. So I would say, hey, 2 times what would equal 12? The answer would be 6, right? So I found a prime number. I'm going to go ahead and circle it. Then I have the 6. Is 6 divisible by any prime numbers? Well, yes, it's divisible by 2 and 3. So I'll go ahead and divide by 2 again. 2 times 3 would equal 6. And then I've got a prime number here and a prime number here. Once you're done circling, once you've got only prime numbers, you're done with the factor tree, which means that 12 would be rewritten as the factorization of 2 times 2 times 3, and that would equal 12. Our final answer is going to be this right here, right? And that's how the factor tree works. Now, what if I was going to use a division tower? Well, I would pick a prime number, 2. 2 goes into 12 6 times. Then I divide again. And 2 will also go into 6, so 2 will go into 6 3 times. And once, the way the division tower works is when your top nth number finally becomes a prime number, you're done. So that means this is my division. It's going to be 2, well, this is my factorization, 2.2.3, which is the same answer we got over here. So you can use towers to divide, or you can use factor trees. Now, when you're using factor towers, you have to make sure you divide by prime numbers. However, division trees are not nearly as strict. So for example, I could take the number 12 and I could divide by a non-prime number. I could divide by 4 because I know 4 goes into 12 3 times, right? Once I divide, I look for primes. I know 3 is prime, so I'm going to circle it. 4 is not prime. So I divide 4. 4 gives me 2 times 2, and now I've got 2 prime numbers, and I still have the same answer. 2 times 2 times 3. So I prefer factor trees because they've got a little more room for error if you accidentally divide by a non-prime number. As long as you work to get prime numbers at the bottom of every tree, you will be correct. But some people like division towers, and if you like division towers, that's great. The only thing you have to make sure is that you're always dividing by prime numbers. Okay? That's it for this lesson. If you have any questions, let me know on the school website, and I will see you in the next class or video.